Hello friends, welcome back to my channel Engineering Mathematics DJ Ganit. From this lecture onwards, we are going to discuss about numerical methods for solving roots of equations. We know that suppose we have this type of equation, say quadratic equation x square plus 2x plus 3 equal to 0, then we can find out value of x which satisfies this equation simply by that standard formula x equal to minus b plus or minus square root of b square minus 4ac divided by 2 times a, where this ab and c are these constant coefficients. Coefficient of x square is a, coefficient of x is b, and c is the constant term. So this direct formula is available for quadratic equation. For linear equation also we can easily find out root of this equation, that is x equal to 3. But suppose we have a higher degree polynomial equations. For example, suppose I have this type of equation x cube minus x plus 1 equal to 0, then we are not having direct methods for solving every cubic equations, and suppose degree is getting higher. For example, if we have 4th degree polynomial equation, then we are not having direct methods. So in those type of situations we have to go for numerical methods. Sometimes our equations may involve this type of non-algebraic functions also. Suppose I have this equation x minus cos x equal to 0, then direct methods are not available. I can have this type of equations also, x times e raised to x plus sin 5x equal to 0. So all these equations are not solvable by direct methods. We are not having any direct methods, or we are not having methods for solving these equations directly. So for that we require numerical methods. So from this lecture onwards we are going to discuss methods for solving roots of equations, especially this type of equations, higher degree polynomial equations and equations which involve this type of transcendental functions. This cos x, logarithm of x, all these functions are known as transcendental functions. So first method we will start with is bisection method, and we are going to use this bisection method for solving this type of equations, function of x equal to 0, where fx is a function of single variable. So mainly if fx is a function involving non-linear polynomials or non-linear polynomials of higher degree, or suppose our function fx involves transcendental functions, then we have to go for numerical methods, and we are having some numerical methods for solving this type of equations which we will discuss one by one. So in this lecture we will focus on bisection method for solving this type of equation fx equal to 0. Now before going for bisection method, we discuss one result which is true for continuous function. That result is known as intermediate value theorem. We will require this result to understand the process of bisection method. So what this result says, that suppose we have a function f which is a continuous function. For example, we can sketch graphically also. Suppose I have this type of continuous function, that is its graph has no breaks. Now suppose we can find out two real numbers, say a and b, such that value of function at point a is positive or suppose negative. Suppose this point is a, then we can see this distance is value of function at point a, and it is below x axis. so it is negative. So suppose value of function at point A is negative and value of function at point B is positive. So suppose B is somewhere here. If B is this point, then this distance is f of B and it is positive. Then we can see our function fx intersects x-axis at this point. So at this point is on x-axis, therefore value of y is 0 at that point, and we are considering y equal to fx. So at this point fx is equal to 0. So this is the root of equation fx equal to 0. So intermediate value theorem says that if we can find out 2 points A and B on x-axis such that value of function at those 2 points is of opposite sign. If f of A is negative, f of B is positive, and another situation is we have to find out A and B such that f of A is positive and f of B is negative. That means f of A and f of B are of opposite signs. So if we take the product of f of A and f of B, that product is always negative. Then intermediate value theorem says that the root of this equation fx equal to 0 always lies in this interval. So this is the search interval for exact root. We call this interval as search interval. This result says that suppose we have a continuous function fx. If we can find out two real numbers a and b such that f of a and f of b are of opposite sign, that is if f of a is negative, f of b is positive, or if f of a is positive, f of b is negative, then the root of fx equal to 0 always lies in the closed interval ab, or root lies between a and b. So this theorem gives us the guarantee that the root is always in between a and b such that f of a is negative and f of b is positive, or f of a is positive and f of b is negative. So this gives us the guarantee that root always lies between these two numbers. So we can try to find out approximations to the exact root. So this is the idea of bisection method. First you find out two real numbers a and b such that f of a and f of b are of opposite sign. Now once you find out a and b, you consider first approximation as average of those 2 points a and b. So x1 is nothing but middle point of the interval ab. So find out x1 as average of a and b, that is x1 equal to a plus b by 2. So x1 will be somewhere here. Now here f of a is negative and f of b is positive. In this situation for which we have sketched this graph, f of a is negative, f of b is positive, and we find out x1 as midpoint of the interval ab. Now find out value of function f at x1. So we can see if we consider this perpendicular line segment, this point is x1, so we can see f of x1 is positive. This distance is f of x1. Now f of x1 is positive, so you check that for which value your function has negative value. So we have seen that f of a is negative. That means now our search interval reduces to interval a to x1. Now I can say that root lies in between a and x1 because f of a is negative and f of x1 is positive. Root cannot lie between between x1 and b because f of b is also positive and f of x1 is also positive. So now we will consider next approximation as average of a and x1. So suppose I consider a plus x1 divided by 2. That means now I am taking midpoint of the interval a x1. So suppose x1 is somewhere here. This is now x1, not x1, it is x2. x2 is the average of a and x1, that is midpoint of the interval a to x1. Now again we check value of function f at point x2 and we can consider this distance. So now we can observe that f of x2 is negative. So now x2 is average of a and x1. So we will check for which point function has positive sign. F of x2 is negative. So I have to check whether f of a is positive or f of x1 is positive. And here we have that f of x1 is positive. So now root lies between x1 and x2. So we will consider next approximation x3 equal to average of x1 and x2, that is x1 plus x2 by 2 is this point, midpoint of the interval x1 and x2. So we will follow this procedure and we will go up to desired accuracy. In questions they will ask you to find out root of given equation correct up to 2 decimal places or 3 decimal places. So we continue in this manner and we stop when we get two values are equal up to required number of decimal places. Suppose value of x2 is say 2.34 up to 2 decimal places and value of x3 is also 2.34. Then we stop and we write that root is 2.34 correct up to 2 decimal places. So depending upon the question we have to fix decimal places in our calculator and we have to continue this process to obtain this type of approximations to the root. This is the idea of bisection method. It is very easy. First you find out search interval, that is you find out by trial and error 2 points A and B such that they are of opposite side. Then you consider first approximation as average of A and B. Then find out value of function at that point x1, and if f of x1 is positive then you check that for which point function is negative. x1 is the average of A and B and f of x1 is positive, so you find out that point for which function has negative value. So here we know that f of A is negative. So we will consider next approximation as average of A and x1 and that we will denote by x2. Similarly we find out f of x2. So we find that f of x2 is negative and x2 is obtained by taking average of A and x1, and because f of x2 is negative I will check that function is positive for which value, either for A or x1, and I know that function is positive for x1. So I will select next approximation as average of x1 and x2 and I will continue in this manner to obtain my root up to desired accuracy. So that is the idea of bisection method.